Okay, good afternoon, everyone, and welcome to designTimber. My name is Barney Jordan, and I'm the Editorial and Events Coordinator at Timber Development UK, and will be your host for today's webinar. This will be the 7th session in our 2024 series of designTimber, in which we hear directly from the multidisciplinary design and delivery teams behind exemplary timber buildings, selected from the 2023 Wood Awards shortlist and winners. Today, we will be learning about the Eton Sports and Aquatics Centre. But while people are still arriving, I'll take a couple of minutes to tell you a few things about Timber Development UK. So TDUK was formed in 2021 to bring together and support the entire timber supply chain. We represent everyone from supplier to specifier, including architects, engineers, contractors, craftspeople, and all points in between. And here you can see TDUK's 3 key missions. One of the many ways that we seek to deliver on these is with our designTimber talks, through which we hope to educate, inform, and inspire designers and other built environment specialists to build better and lower carbon using intelligent timber design. If you go to our website, you will find a wide range of other timber knowledge resources. This includes designTimber, our regular print magazine, a library of technical case studies, and our timber knowledge sheets, which cover essential topics such as fire-safe design, acoustic regulations, and timber connections. While many of our resources are available to all, there are a host of great benefits to becoming a member. For those of you who are not already, we would love you to join us. Not only does this benefit you and your business, but it also supports us to continue to put on free educational events like this one today. And now today's session. I would like to welcome our speakers for today's webinar, who are going to tell us about the Eton Sports and Aquatics Centre. We are delighted to have Andrew Barnett, Principal at Hopkins Architects, Barney Jordan, Structural Engineer from Cundall, and Timber Specialist John Spittle from WIEHAG. We will hear a presentation from each of them, and then hopefully we'll have time at the end to ask audience questions. So during the presentations, please do make use of the Q&A feature, which you will find at the bottom of your screens, to note any questions that you would like to ask. And I would now like to hand over to Andrew for his presentation. Thank you so much.
Thanks, Barney. Okay. Can we see that? Can we see that? Can we see that?
Can see that, Andy.
Yeah.
Okay. Hi, everyone. So I'm going to give you a sort of broad introduction to the project. One in 2017, built during COVID, finished in January 22. This is not Eton and it's not timber, but it is our office patera system that we currently occupy. It's just been celebrated its 40-year anniversary, and I just thought it was quite interesting because in thinking about the project recently, it sets a whole number of themes, which actually is quite interesting to see how its genealogy has kind of lasted through kind of 40 years of practice. So this was a patera system, light industrial system designed by Michael and Patty Hopkins in the 80s. It's a dry construction. Everything's prefabricated, so it's super accurate construction. It is a kind of simple rectangular box form, so that the sort of simplicity of the form lets the construction read through, and the craft of the building becomes, if you like, the sort of architecture of it. It's also, this one was built in the Docklands, sitting right by the waterfront. I never visited this building, but Patty talks about how that amazing fully glazed elevation, so no punched windows either, it's just, you know, the glazing becomes an entire facade. And she talks about how it really sort of unites the kind of the interior of the building with that kind of waterfront setting. And then perhaps most importantly, the idea of that kind of independent expression of structure and envelope, giving a kind of real legibility to the way that the building has been designed and engineered. So the story of Eton for us sort of starts with understanding a bit about the history of swimming at Eton. And back in the day, the boys used to swim in the Thames on a bend of the river called Athens. Hence, the name of our building now is called the Athens Pool and Sports Hall. The site of it is on the right of the screen here, where they built an outdoor swimming pool, which they had for many decades, sitting slightly out from the main campus of the building, so the main campus of the college. So the college is off to the left of the screen. And you can see that they made this sort of clearing in the woods outside the main grounds of the college. And then they recreated the bend in the river in this outdoor swimming pool. And in this clearing in the trees, they then, from the excavations from the pool, they created a bund or a raised bank, which they planted to become this kind of private swimming place in the grounds of the outer grounds of the college. But they then decided they needed to, decades later, they needed a kind of indoor pool. So they built that, which meant that the old pool fell into dereliction. And here it was, as we sort of saw it and came to the college. And when we first visited, this was the sort of scene that kind of greeted us, of this kind of deserted site surrounded by an overgrown landscape and a dried up and failing external pool. But it did give us the idea of the excitement of the discovery of this site as a kind of lost garden or a kind of walled garden in a country house, where you kind of walk through a threshold and then you find yourself in another kind of place with another kind of feeling. And that's the sort of inspiration of the overall design. And particularly, this is a ground floor plan, the site plan, particularly the idea that of the building's relationship to the landscape, making this sort of clearing in the woods. So you can see the pool on the top of the screen. You can see a sort of central link, and the idea of that link is that it connects a front entrance courtyard with and garden with a rear, more informal garden at the back of the pool, and then linking those two things is this central link through the building, and then on the bottom of the screen is the sports hall. The site is metropolitan open land, so in fact that's when this kind of idea of the timber comes through. In building these big spanned spaces, we had to sort of find a way of an economical structure, building two flat roofs, sinking both volumes into the ground, keeping that roofscape below the trees, so the building is still effectively kind of hidden from the sort of outer landscape and the environment. The really nice thing about that was that the surface of the pool became level with the landscape around it, and with a grand window between the pool and the informal garden, which you can see at the back of that drawing. There's a really nice feeling of connection between swimming in the pool and the landscape, which is of course a reference and memory to the idea of the external pool literally swimming, amongst that landscape. So this is the kind of development of the form from a simple rectangular volumes, split apart and slid apart, with then that link kind of cutting through it, with then a kind of formal series of walls making a garden at the front, a stair tower and a lift tower, celebrating that sense of arrival. And then the idea of taking these simple volumes in brick and then cutting holes into them to enable that relationship to read through between the internal environment and the landscape around it. And here's the grand sort of section through the building. These big double height columns through the pool, you can see it level with the garden. These big glulam spruce columns marching along the pool at 4-meter centers and forming this flat roof sitting below the kind of roofscape. So really kind of simplifying the building like Patera in a sense to these sort of 3 or 4 kind of elements: the structure, the glulam, the brickwork envelope, the glazing, opening the building out to the landscape, and the landscape itself, of course. And so from kind of concept and design to finished product, this, you know, I feel it's a very kind of clear development. You can see there in this photo of the finished building between the timber structure, these massive 1.6 glulam beams that span across the whole width of the pool, and then opening out that western elevation to the informal garden beyond. So if it's informal and open on the one side, it's much more closed and solid building as you enter it. The idea of the stair tower marking the entrance, the sports hall slid back to make that front garden, where you get the first sense of the connection with the timber coming through and that glulam structure kind of marking the entrance to the building. As you walk through, you get this double height space that links the front garden with the rear garden, and you get the grandness of the scale of the glulam structure, cut open at roof level with these linear roof lights to bring daylight and sunlight into the building, really kind of animating what can often be in this typology of building a sort of simple sports shed, but really kind of thinking about it as raising the kind of opportunity to raise the environment of the pool and the hall. And as you rise up the stairs to the sort of viewing gallery above, you then get this kind of really intimate relationship with this kind of grand scale of structure that surrounds these volumes. You can see on the left-hand side there the idea of separating the envelope, the brickwork, with the glulam structure. They're separated by about 10 inches, 200 mil, which really does have a kind of significant effect when you see that from the interior of the two sporting volumes. And you can see it there in the way that the sunlight animates the shadows and light on the wall of the brickwork. You can see that little kind of thin line of sunlight between the glulam column and the brickwork beyond. And you can see these brave sort of structural openings that we made into the brickwork, connecting the interior of the pool with the landscape bund, just newly planted in this photograph, now much more mature and green, keeping that idea of the relationship of swimming to the outside landscape surrounding the building. And then up on top of the changing rooms, which there are two types. So the community, there's a community swimming pool, changing room for the public, and there's a team swimming pool for the boys of the college. Making this kind of roof, this deck on the top of this changing room, looking down into both volumes. And the idea of creating a building that's not just about sort of varsity sport and really, you know, competitive focused sport, but a place to actually kind of enjoy and be a different sort of place to the environment of the central campus of the college. So the structural timber is obviously glulam. CLT spans between the glulam columns and beams. Then there's sort of non-structural timber. These are the ash. We made these ash seating for the gallery to look down onto the pool. They were inspired by Mersey ferries in Liverpool, which used to have these wonderful kind of life raft benches on the upper deck of the ferry boats. So the link obviously is this linear void between the two sporting volumes, which, as I say, links the two garden spaces, but it also works in the opposite direction between the gallery above and the sports hall below. So you can see that actually it forms a kind of informal spectator gallery to the sports hall, from the upper deck to the cantilevered stair to then the ground floor link. You get these kind of three sort of almost free spectator galleries looking down into the hall. And then the hall sunken down, so it provides that birch face ply, provides a reflective surface for bouncing balls off on five-side football. And then because that's at ground level, you then get another window which kind of looks out onto the landscape beyond and brings daylight into the heart of the building. And finally, the informal garden, where the building, both volumes really kind of open up, finishing that story of the relationship between swimming at Eton in a green landscape. And I hope what we've made is not some dumb boxes, but something that's intimately connected to both the history of swimming at Eton and intimately connected to its place in the landscape and the college campus. Thank you very much. That's a brief intro to the project.
Well, thank you so much, Andrew. And to Barney next.
Just share my screen. Is that okay, Barney? Can you see that? Excellent. Afternoon, everyone. My name's Barney Jordan. I'm a partner at Cundall and primarily a structural engineer for this project. Over the years, I've had the privilege of doing many collaborative projects with Hopkins. So this is just the latest in a series I've done. On the right-hand side, you can see the new music school we did at King's College School, Wimbledon. And on the left-hand side is a project we just finished at Wimbledon for the All England Lawn Tennis Club, their new indoor tennis centre. So I've worked an awful lot with Hopkins. I've worked an awful lot with Andy, and that's helped us develop a sort of relationship that I think has been very helpful in terms of delivering this Eton project. Tiny little bit about Cundall. We are over 1,200 people now, and we have 26 offices dotted around the world. In terms of the disciplines we offer a big range of basic core engineering disciplines, but also an awful lot of specialisms that have been utilized in this project. So in no particular order, we've done building services, acoustics, civil engineering, fire engineering, geotech, lighting, sustainability, and most importantly, structural engineering on the project. But it's meant that it's been a really collaborative effort and a multidisciplinary effort across the entire piece. Obviously, this talk is mainly about the timber elements of the building, but I thought it would be useful to set the context, and I think what Andrew said actually is useful in terms of the overall vision for the building. But I'll talk a little bit about the site constraints, the form of construction that meets those challenges, how it's designed structurally, and some of the detailing and design of the timber roofs. And most importantly, the fact that this is a team effort. We've had a lot of collaboration between the architecture, the contractors, the construction, and the engineering on it. The site in Eton is a challenging one. It's near the river. It's near a number of rivers. It's in flood zone 3, which means that it can fully flood, and we obviously have to allow not only for today's conditions, but what might happen due to future climate change. On top of that, there's a challenging geotechnical stratigraphy and also a very high groundwater table in the area. This actually sets two challenges. As Andrew mentioned, that the idea was to push the buildings down into the ground to slightly mask the sort of the building mass. But of course, doing that has a number of engineering challenges. The first being in the long-term design condition for the building, we actually have to stop it floating out of the ground, and that's particularly pertinent with high groundwater level. And in the event that we get a major flood in this area, the building would literally want to try and pop out of the ground like a boat. So that's one of the challenges we faced, holding it down. The other one was to do with the fact that during construction, we had to excavate and remove the existing swimming pool structure, and then dig a large excavation into the ground and keep that dry enough so that they could build the new structure. The substructure is formed of in a secant piled wall box. The piles go down to a stratigraphy that's basically fractured chalk. It's not often in our region, southeast of England, we get into clay, which forms a nice seal against groundwater level. But the fractured chalk actually means that water will continue to flow through the ground into the excavation as you build it. And to counteract this, the main contractor, who are Graham Construction, set up an array of well points across the building footprint. These they basically extract water out of the ground. They pump it to a remote location, and part of the Environment Agency's conditions on this was that we re-injected the groundwater back into the ground in well points remote from the site. So there's no actual net lowering or raising of the groundwater in any sense in this area. Above ground, as Andrew mentioned, that the facades of the building are largely punctured with big openings to form, allow light to come through and glazing to be formed, and it's particularly noticeable that there's sort of complete open on the east elevation of the sports hall, and there's a very, very large opening on the east elevation of the pool and down the side. So to achieve this, we came up with a very clear structural diagram, and it's basically we've provided thin, slender, reinforced concrete walls that not only restrain and support the brickwork, but they also act as shear walls to provide overall stability for the building, but they as another function that they act as deep beams. So I don't know if you can see my cursor, but the one on the right-hand side of the pool, there's a very large slot cut in that so that the wall acts as a very deep beam to span over that. In the sports hall, these ends actually act as a deep cantilever. The roof structure is basically is formed of glulam beams supported on perimeter columns at approximately 4 meter centers. So these beams act to laterally restrain the concrete walls in about the minor axis of the concrete, and they also then the wall then in turn provides lateral restraint in the long direction. So they're acting as shear walls. The stability diagram for the pool, the buildings relies very much on the fact that you've created stiff walls to form a box and then a rigid diaphragm to join all the walls together. For the sports hall building, this was particularly tricky actually, because we've only got walls on 3 sides, which normally you would, a good stability diagram has walls on opposing faces, and it's more like a big rigid box. This diagram still works, but you do very heavily rely on the roof acting as a rigid and strong diaphragm. So as part of the design, we introduced in-plane bracing into the roof to help transfer those forces. Interestingly, once WIEHAG were on board as a contractor for these elements, we worked very closely with them, and we were able to actually justify the fact that the CLT roof panels were strong enough and especially stiff enough, combined with their fixings, to allow us to eliminate this bracing. Now, so obviously that afforded a cost and a program benefit to the project. This image just shows the CLT roof panels in place. It's worth noting that the CLT doesn't always reach the perimeter walls, and there's these large slots cut into the roof, which is also part of the roof-like glazing system. Because the 2 buildings are effectively independently stable, we actually had to structurally introduce a movement joint down the link building that Andrew talked about. That came with its detailing challenges, as you can imagine. Just talking about the different design conditions of the 2 buildings. So starting with the sports hall, on the roof we had a green roof, and there's quite a number of suspended sports equipment stuff on the underside. So the roof had to be designed for the loading of that. The environmental conditions in there are fairly benign actually. So it's a service class 1 design condition for the timber and corrosivity category C2. The pool, on the other hand, is very different. So that's we designed that as service class 2 and corrosivity class 4. And the roof to this also supports an array of PV. It's worth noting that some of the timber actually passes from inside to outside, and there's a projecting cantilevered canopy along here, and also above the entrance area that was shown in some of the earlier images. Timber obviously is very good from this perspective because it's inherently durable, and it also doesn't suffer in the same way that timber or steel or concrete would in terms of needing thermal breaks. As I described, the stability diagram for the building, I mean, this is just showing the pool hall as an example, but it uses the shear walls around the outside of the building, the roof acting as a rigid diaphragm. This slot down the side of the building is actually structurally a bit challenging because the diaphragm doesn't actually meet the shear wall that it relies on. So we actually had to design these glulam beams to take the diaphragm force in minor axis bending back to the concrete wall. This is just a general cross section across the two buildings. The sports hall is approximately 20-meter span with a 80mm thick CLT decking on it. The beams there were 320 wide and approximately 1200 deep. The pool hall is a much bigger span. It's 31 meters with a thicker CLT roofing on it. The beams there are circa 1700 deep. All the glulam beams and columns were grade GL28C. I just thought it'd be worth talking about a little bit about some of the detailing here. These drawings are from our design drawings. It's worth pointing out that post-contract, we work very closely with WIEHAG to refine these details to suit their preferred methodology and also to take benefit from their specific expertise in how you join bits of timber together. This detail on the left-hand side here shows the connection that Andrew was talking about, where there's a distinct gap between the glulam and the brickwork and the concrete wall behind. So the way this works is the column has a sort of L-shaped rebate cut into it, which then means that the beam sits directly on that. The load from the beam is then transferred in bearing directly down. The bracket detail that you can see here connects the concrete wall with the end of the glulam beam, but it acts as a lateral restraint to the concrete wall in the left to right direction, but then the concrete wall acts as a lateral restraint to the glulam in the into the page direction. Another subtle requirement of this is that whilst the glulam is laterally supported at the top flange by the CLT decking, we needed to provide torsional restraint to the glulam beams at the ends in order to resist lateral torsional buckling. And this detail was the way that we did that. Another key detail is the way that we detail the base of the columns in the pool area, because obviously there's going to be a lot of water splashing around when they wash it down. So we actually devised a seating detail that actually elevated the base of the column off the pool deck, and then it's clad, you can see it in the photo, it's clad with a nice protective detail. The link building, again, as we were talking about, it's got a flat roof here. It's partly CLT decking, it's partly glazed. They're supported on very slender flitched beams, which span between the sports hall and the pool. At the interface with the pool hall, we had to introduce a movement joint, which again, it added to the complexity of it. But I think the visual intent that we matched actually has worked very well in this instance. One of the key challenges structurally for us was actually working out how much these roofs would deflect during, early stage in their lives and over time, how they would creep. There's particular challenges where these interface with other elements of the building. So partway along the viewing gallery, there's a full height glazed screen that interfaces with the building, with the roof beams. So we actually had to work out how much the interface detail would have to deal with in terms of deflection and tolerance and all those sorts of things. Now this calculating pre-cambers on these big timber elements is really tricky. It's part calculation, it's part black art based on experience. And we worked very, very closely with WIEHAG to come up with a strategy for pre-cambering. This photo bottom left, you can't really see it, but it actually shows the beam lying on its side, and you can just about see the pre-camber in it that was needed. So the idea is that you erect the beams, you put all the load on it, and by the time they come to install the glazing, it's in a predictable position, and then the interface with the glazing then can accommodate the further movement that will happen over time. I've mentioned collaboration with WIEHAG a lot, and it was actually a really important part of this project. Whilst we did all the initial design ourselves, when they came into the project, and I have to say they were very helpful even before they were in contract. We discussed material grades, exact section dimensioning, transportation and handling, and I know John will talk a bit about this, but transporting a 1.7 meter by 31 meter long beam across a lot of Europe and then erecting it is a really challenging thing. So we had to understand if that actually could be physically done. I've talked about diaphragm actions, connection design, pre-cambering strategy. And the other thing they advised the design team on was the build up and change of temperature and humidity in the pool building once the envelope is enclosed and the building has got water in it, because obviously you don't want the conditions to change so rapidly that you cause splitting in the timber. So that was another aspect where we really relied very heavily on their expertise. At that point, I think I will hand over to John, who can talk about the WIEHAG aspect of the project.
Thanks, Barney. Okay, I'll just share my screen. Hopefully you can see my screen, everyone.
Yes.
Grand, thank you. Okay. Good afternoon, everyone.
We can't see your screen yet.
Oh, you can't? Oh dear, sorry. Hopefully it's working now.
That's great. Thank you. Sorry.
Okay, thanks. Sorry about that. Yeah, thanks. Firstly, a brief introduction to the company on there. WIEHAG, a long-established volume glulam manufacturer that started making glulam in the 50s, and really by constantly pushing the boundaries, we're acknowledged as being one of the industry pioneers with this versatile product. WIEHAG's still family-owned and are constantly reinvested in the business, as is illustrated here on the right, where you can see we've recently put in a new 3-story office block and new hall, all in timber. This is our state-of-the-art factory in Northern Austria, and it's situated near the suitably managed European forests, which really enables efficient logistics and supply of the key raw material. Like most large European glulam and CLT manufacturers, WIEHAG have their own on-site power station, which runs solely off our waste timber. And this makes our entire production self-sufficient for heat, and over half our electricity comes from our on-site solar energy plant. Consequently, we're not affected by volatile energy prices to anything like the same degree as other products such as steel and concrete. Yeah, WIEHAG are not just a project management company or supplier. We offer the detailed design, manufacture, supply and installation, and this includes providing cranes and mutes. So this makes us look at a package in a much more holistic manner, which is really important for achieving successful completion on sort of complex projects like the Eton project. We've been successfully delivering numerous groundbreaking projects around the globe in a variety of sectors for a good few years now, and we're constantly seeking to raise the bar in terms of scale and complexity, while still retaining sort of core values like quality, safety, service and value. Just to give you a bit of an idea of our capabilities, we simultaneously manufactured and delivered the glulam members and connections to both the largest timber building in Asia and the world's tallest hybrid timber building. And all of this was carried out during the pandemic with the added distraction of a ship getting stuck in the Suez Canal. Introducing the package that we did, the scope really. Andrew and Barney have talked through the architecture and engineering, so really I'll touch on other aspects of this great project. And really, I think as Barney has sort of touched on, the importance of having the right team. And for this project, it really was spot on. You know, and in addition to the collaboration, the early engagement of key subcontractors, such as people like ourselves, I think really did help the project in spite of all its challenges. So I think it was late 2018, we began providing initial design and cost input to the team and assisted them in developing the design. And then there was a really rigorous tender process, ending us being appointed with Graham's in early 2020. And we then commenced detailed design process in collaboration with the design team and Graham. And this included providing a large scale mock-up to the glulam and the CLT. Scope of our works consists of the detailed design, supply and installation, the glulam columns and beams, CLT roof slab, the glulam benches and louvres, plus steel members, including the sort of hybrid flitches on there. Maximum prefabrication was used on all components, with all metalwork connectors and flitch members being factory assembled, and roof beams included factory-made notches to incorporate the M&E services. As illustrated here, this results in a really high quality and high tolerance product, much more than can be achieved by assembling these on site, as well as enabling very sort of fast and safe installation. So really the package comes to site like a giant IKEA flat pack kit. However, it's really important to note that this is an industrial product. It's not a piece of furniture grade joinery, but we think it's the sort of highest quality that can be achieved using such industrial processes. The timber package comprised of about 275 cube of glulam and 170 cubic meters of CLT. And this is all delivered in only 15 lorry loads on a just-in-time basis to suit the restrictive nature of the site. And really using off-site construction greatly reduces the amount of transport journeys, as well as reducing number of site operatives, reduce the noise, dust and waste. And this is really vital on a live education site. As Barney has mentioned, the longest elements were these 8 glulam beams over the pool roof, and they were just over 30 meters long. And this really highlighted how for each project, logistics and access must be considered at an early stage to ensure that they can be safely delivered and installed. And delivering to this tight site was really only possible with close collaboration with the whole team and including our logistic partners, which in this case were DFDS, Special Logistics. The delivery and installation started in late November 2020 and was completed in February 21. So apart from taking place in the winter, it also took place during the Brexit transition, which was quite interesting, but we succeeded in that. And also the full pandemic lockdown. And we were only able really to successfully achieve the installation by working closely with Graham's, our installers, logistic partners and suppliers on there. The structure also included concrete walls, which have different tolerances to the timber package. So the sequencing and interface had to be really carefully managed between the different packages by the team members to ensure the sort of seamless, safe installation without damaging each other's product. And really, there's no point in making a good product if it's not installed properly on site. So WIEHAG ensure we only use the best installers. And on this project, Steve Coleman did a great job, especially considering the various challenges that the pandemic brought. And Graham's management on site during the installation really was vital in making this happen. WIEHAG also provided the structural steel package, which, as well as meaning there's only sort of one warranty, again gave the whole installation process much more efficient. And this included the factory assembled steel timber flitch members. And by assembling those in the factory, it gave a really good quality finish to that. You know, glulam has always been like a go-to choice for roofs in aggressive environments such as swimming pools, because of its natural resilience, and it doesn't require expensive coatings or claddings, but it's still subject to a number of different factors. The timber package, as well as the external roof and wall build-up, have to be properly detailed and installed. and the correct environment must be maintained in the pool hall throughout the year, and a maintenance regime must be followed. And if this doesn't happen, problems can occur. It's often wrongly perceived that engineered timber products are high maintenance, but for projects like this, where most of it's in service class 1 and 2 environments, maintenance is generally limited to just yearly visual inspections for the entire design life of, say, 50 years. And to assist in this, we had created an extensive O&M manual for each project to help inform the end user on how best to commission and maintain the building. And these inspections are vital. It's a bit like when you're at home. If you notice a leak in the roof and deal with it promptly, the effects are minimal. But if you leave it, it just gets worse. Moisture ingress during installation is probably one of the sort of main challenges with this form of construction, and it can't just be down to one member of the team to solve. WIEHAG put a lot of energy into their part of minimising this risk, and this takes the form of various temporary protection measures, including coatings, wrappings and taping joints. Plus, as soon as WIEHAG had completed their works to each area, the roofer puts down the VCL and making sure that it's applied on a dry surface. More recently, WIEHAG have started putting factory-applied membranes, products such as WetGuard, on the top surface of all CLT floor and roof slabs as standard, and this offers an additional level of protection. You can also see here how barriers are fitted to the CLT slabs on the ground so that they instantly provide leading edge protection once the slab is installed. Hopefully this helps demonstrate how WIEHAG don't just get involved in the structural design, but also put a lot of effort into detailing and building physics of the structure. And this helps ensure the maximum lifespan is achieved with minimum maintenance. Due to the nature and setting of this new structure, quality and finish of the product was of paramount importance, as most of the timber structure would be left exposed. And we're only able to meet these high expectations, Hopkins and Cundall's design, through the use of off-site products. Just wouldn't be able to achieve it through traditional methods. Fire is rightly perceived as being a major issue in building design. So on this project, the client appointed Cundall to provide guidance on the subject. They advised that the timber structure did not need to achieve any fire resistance as it just supports the roof. However, each project is different. And on other projects, WIEHAG have designed their packages to achieve 30, 60 or 90 minutes fire resistance. And this is economically achieved without the need for coatings by oversizing the members to create a sacrificial charring layer and encapsulating connections within the timber. This method of calculating predictive charring comes out of the Eurocodes, and we proved it again recently by doing some testing on an 88-metre high apartment block in Milwaukee, where we had provided the glulam and connectors, and had sort of 19 stories of glulam and CLT. And so to address the concerns of the local fire officer and the team, WIEHAG's glulam samples were subjected to a formal 3-hour fire test, which they all successfully passed. This 2-story link, where the end users can enjoy the massive timber elements up at close quarters. Unlike sort of steel and concrete, timber is naturally beautiful and doesn't need claddings or painting. As more and more research is concluding, people do react positively to being in buildings containing natural products like glulam and CLT. You can see here how glulams also form the louvres and benches in between the columns. Items like this are not normally in our package, but it does help illustrate the versatility of this package. We're seeing forward-looking clients looking to improve the carbon footprint of their estates by incorporating low-carbon materials like glulam and CLT, rather than just sticking to traditional materials. However, it's not just a change in material, as timber members will always have a larger section size than the equivalent steel element. This highlights the need for early engagement with specialists such as WIEHAG to ensure the right solutions reach for each project. In addition to clients achieving their CO2 aspirations and complying with government legislation, the fluctuation in price and availability of traditional materials in recent years has certainly increased interest in timber solutions across the different sectors. So really, rather than being just a nice to have sort of option, we think timber is likely to become the first choice on many projects. This is because, as well as being generally sustainable, recyclable and energy efficient to produce, timber is the only structural material used in construction that is renewable. All other materials are finite. So as as the population keeps growing, timber is the only material that can keep pace with the demands of the expanding population. So that concludes my talk today. Thank you very much.
Thank you, John. That was great. And thank you, all three of you. They were fantastic presentations and have provoked lots of questions from our audience. So if I could ask all three of you to put your microphones on and to Jonathan to place a speaker spotlight on everybody. We will go through some of these questions. Just picking up on one of the last things that you said, John, about the motivation of the client on the client's part to reduce the carbon footprint. And I was wondering about with this project, how enthusiastic the client was about the use of timber or their feelings about that as a proposal. And that, whoever.
Yeah, I think Andy probably can answer that better, really, in terms of how the client was on it, because obviously we take Andy and Barney's design, and it's, unless the client is really keen, because we find the key thing now is, does the client want it? And if they don't, then it's unlikely that it's going to happen, because it's always so easy for timber to get kicked out, really, unless the client really wants it. So I don't know, Andy, if you can say what the client's feelings were.
Yeah, I mean, in a sense, the project elevated it itself. I mean, before we arrived, there was a kind of idea that the college were considering of using a bespoke tennis center metal shed, which called the David Lloyd Tennis Centers. But as soon as we started looking into it, you know, we were going to have to change. We were going to have to bespoke it, and it wasn't made for bespoking. It was made as a completely standard system. And I think what I haven't sort of talked about particularly is that the college is, you know, and the site is a very heritage heavy, sensitive setting, and almost more than the central college, you know, where we are, was, as I said, metropolitan open land. So it got unanimously given planning permission. It got supported by Historic England, but it wouldn't have done so had it not been, you know, a kind of sensitively thought out kind of architectural proposal in this kind of green landscape. And the college, you know, they've got a fantastic heritage of brick and timber timber roof structured buildings. So they really engaged with you know, the idea of this building being sort of picking up on that tradition, using these natural materials, the brick and the timber, to create something that hopefully has been elevated from a kind of, you know, kind of rectilinear, sort of simpler shed form, really.
Yeah. And I know that one of the strategies that helped with getting the planning permission was the reduction of the roof level below the tree line. I think we've had a couple of questions about the roof and it being a flat roof, and was wanting to ask whether this required any particular, well, one question was whether it has any fall or is completely flat, and whether it posed any challenges in terms of insurance with moisture management.
I can take some of that. So yeah, when we first started sketching this building, we were sketching you know, pools with big sort of multiple pitches on them. But I soon realized, you know, that we needed to keep the roof line down below the tree line. And from somebody else asked about sustainability. Yeah, you know, on all our projects, we're thinking about sustainability right from the outset. And I had just finished a project of some very big Olympic size athletics venues in America. And we really learned on that project that what you want to do with these volumes, if you want to be kind of environmentally, you know, kind of responsible, is to create minimum volumes, because these buildings require ventilation, they require heating, particularly the pool, obviously. So what you want to do is to create something that has the minimum possible envelope and massing, and of course building a flat roof gives us that. These volumes don't have to be any bigger than they have been designed. Above the flat surface of the CLT is insulation, which is laid to fall, and so both roofs do have a fall on them.
Great, thank you. And there were a couple of questions, Barney, about disproportionate collapse. So one was more specific about the consequent class of the building, but both really asking about the way that disproportionate collapse was considered in the design.
Well, testing my memory a bit, but I think it was considered a Class 2B type structure. It obviously has members of the public in there, but not huge numbers. As a matter of course, we made sure that everything is tied effectively horizontally and vertically. So in terms of disproportionate collapse, it's fairly conventional in that sense. Mostly it's, apart from all the concrete structure of the changing rooms and plant rooms and stuff, it is mostly a roof actually. So by effectively just tying all the components together, it is inherently pretty robust. Is probably the extent of my memory on the topic, I'm afraid.
Thank you so much. And one on the longevity. So is there any indication of what will happen after the first 50 years, specifically with the timber elements?
I mean,
I doubt I'll be around to see it, but
yeah, it's designed for 50-year design life, isn't that right, guys?
It is, yes, and I don't see why, properly maintained, well looked after, this building shouldn't last a lot longer. It's inherently a robust design. It's very well detailed, and I'm sure the college will look after it well. So I'd love to think I'll be around in 50 years' time, but sue me if I'm not. So.
I mean, we've been making sort of glulam since the 50s, and a lot of the structures are still in use today, and a lot of them are industrial halls. And so it is all about maintaining those. I mean, I was brought up in a 500-year-old timber frame house. So whereas there are other timber projects and other forms that fail after a short time. So it is all about that design and detailing and that waterproof envelope. And where you do have flat roofs, that's why maintenance is, that visual inspection is so important. If there is a failure in the membrane there, and just making sure there's not leaves getting stuck in gullies and, quite common sense stuff. But because they've got a good client there that will maintain it, I'm sure it will be there. The detailing is devil's in the detail. And because these guys have really put the energy in, I think the structure is going to last.
And this is a question about the very beautiful shadow gap that you showed us, Andrew. So a question about how this was created between the glulam beam and posts. In fact, this might be a different detail. So what creates the nice 10mm shadow gap between the glulam beams and posts? Is there some sort of steel angle in there, or is the timber rebated?
Oh, I can't quite. That's testing my memory. There's a steel plate, isn't there, John, between the columns and the beams?
Yes. Yeah, that's it. Yeah, the beams sit on the column on a ledge, but there are also steel connectors within them. You encapsulate all those connectors in there to try and give minimum metalwork being visible. But yeah, it's that really nice crisp detailing, and where people do want shadow gaps, incorporating them. And when you manufacture those glulam elements, they're made to 1 or 2 millimeter tolerance. And that's really the key, to give that nice crisp detailing, that you can make these really big elements to really tight tolerance. But obviously when they fit together, you do get some creep in there, but it's yeah, as I say, it's been a couple of years since we've all been working on the job at that detail, Barney, isn't it? It's trying to remember the exact detail.
Yeah, you're absolutely right.
This might be a bit of a technical. This is a question for Barney, which I will read out as it's written because I'm not sure I can interpret it too well. So how did the structural engineers deal with the lateral ground pressures around the basement air duct? Continues, and in the general arrangement section, it looked as though those pressures were applied onto the pool shell. Is that correct?
It's a very good question, actually. We generally, all the earth pressures are dealt with by a cantilever retaining wall. So it's like an embedded secant pile wall that just cantilevers. We didn't rely on the pool deck to laterally restrain the head of that wall, because there'll be points where in the diagram where it just doesn't balance across the site. So generally it was all done by a cantilever action, so that the earth pressures are not transmitted into the pool box as such, if that explains it clearly.
Thank you. This is a question about moisture exposure protection. So was there any moisture exposure protection, UV protection, or protection against biological factors to mitigate fungus?
Yeah, I think it's, again, a good question. The service class determines what coatings we put on. We don't want to put unnecessary coatings on, but in the factory, we put sweeter coatings. So if it's service class 1, it can be limited just a aqua varnish, just to protect the timber from moisture ingress during installation. Service class 2, you can have a whole suite of ones, including anti-fungicides, blue stain, rot, and they're all surface applied in the factory, all clear coatings. And really, once they're on for life. They don't have to be reapplied. The only coatings that might need reapplying are ones in a service class 3 environment, you know, totally open to the elements, because the sunshine and the rain will leach off within a few years in UK climate, any surface applied coating. They're not vacuum impregnated. But I think on all the sort of pool and the sports hall ones, all service class 1 and 2. So all the coatings we put on will last the whole design life, unless they're in really heavy traffic areas, like some of the columns. So during that maintenance period, if some of the coatings are being seen to be in sort of scuffed off, what have you, then during the maintenance, just reapply coatings there. So that's why the maintenance is so important to maintain it.
Thank you so much. And we don't have so much time left. There's one question which was out of interest. What was the camber on the beams?
I think the main span over the pool hall was circa 120 millimeters, and I think the sports hall was about 80. We spent an awful lot of time debating what the right number was, and it's partly due, to do with, do you take the short-term deflection plus a proportion of the long-term deflection? How much load because whilst the roof is obviously designed for 0.6 kilonewtons per meter squared access load, that hardly ever happens, and all those sorts of things. So, but I think, John, I doubt you'd remember either, but I think it was 80 and 120.
Sounds a lot, but over a 30-meter beam.
Yeah.
Yeah, it is, as you say, a really interesting thing about pre-camber, because if you pre-camber it too much, it's difficult to fit the CLT sheets on. And then when it gets its full loads, those CLT sheets aren't fixed in the right thing. So it is a lot of collaborative, to a lot of people talking, and from all different levels, really. There's not one person that decides, on these, when you get something this special. Yeah.
Just out of interest, we had a particularly difficult condition in that the end wall is almost like continuously supported, but the penultimate beam obviously is simply supported over its entire span. So we had to think about the differential deflection between those two elements and how to make sure that the cantilever that projected outside the pool wasn't dipping down or poking up. So a lot of effort went into that, but based on the photographs, it seems to have worked fairly successfully.
Great. Well, thank you so much. I think we have just about come to the end of our time. So I'd just like to say, a big thank you to the three of you for sharing this project with us, and also to our audience for asking such interesting questions. I'm just quickly, before we leave, going to share a final little bit of information about our next webinar, and in fact, the final one in this series. So the next session will be on Wednesday, the 11th of September, and we'll be focusing on the new headquarters of the National Manufacturing Institute of Scotland, an educational facility which has been constructed with a prefabricated diagrid glulam structure intended to communicate the Institute's values of manufacturing innovation and sustainability. So if you would like to join us for this one, please do go to our website and sign up. And these are a few images to entice everyone. And I would just like to say a final thank you again to our speakers, and I hope everybody has a lovely afternoon.